topological sort solves the dependency ordering problem. So what is dependency ordering? So consider, suppose you want to compile a library. And very commonly, like, a library has dependencies on other libraries, right? Which means that those other libraries have to be compiled first. So you have a bunch of tasks such that those tasks have a dependency on previous tasks. Like, the previous tasks have to run first. So let's say you have a library A, and it depends on library B, C, and D being compiled first. But then library D actually also has a dependency on library C. So think about, like, B and D are kind of like high-level libraries, but C has a bunch of shared utility functions. And therefore, all of these libraries depend on it, right? Because C is the common shared utility functions. So A uses them directly, but also B and D use them. And then A also happens to use these high-level libraries, B and D. You know, this is a web server library, and this is like a library for running graph algorithms or something. And this is a bunch of utility methods. And then maybe this one uses the standard library, and so does this one. So you might have like some kind of flow like this, and you want to determine what is the order in which this needs to be compiled in order to be valid. Valid means that when you solve or when you compile a library, all of its dependencies have already been compiled. So, kind of first like a theoretical question. Is this always possible? What do you think? Yes? No? No. This is not always possible. What's a case where this is not possible? Exactly. So it is not possible if you have a cycle. Because, why not? Well, we can prove it rigorously. It's easy to prove it rigorously. Okay, so first of all, let's consider what is our desired output. So we want to get some topological sorting S, and S is basically an array that contains every node in the graph exactly once, in such a way that the array represents one possible sequence in which the tasks can be validly executed, right? So in other words, if a particular node occurs here, for example, if B occurs at this point, then it should be that all of the dependencies of B have already been covered here. Either B should have no dependencies, or all the dependencies of B should already have been covered earlier, which means that B is ready to compile because all of its dependencies are ready. So, now you can really understand why it can't be that this graph has a solution. Without loss of generality, assume that A is the first, or without loss of generality means I could have made this argument with B or C, it doesn't matter. Assume, consider the first of these nodes that appears in the sequence. For example, it's A. It could be B or C, right? Now, every node in this cycle has a dependency on some other node in the cycle. Now, what does that mean? That means whichever one of these nodes occurs first, it had a dependency on every other node in this cycle. But the hypothesis was that this is the first node in the cycle appearing here. We're basically saying, scan any proposed output and find the first occurrence of one of these nodes in the cycle. Let's say it's this one. It is definitely the case that A does not have its dependencies satisfied, because A was the first node in the cycle to occur, and every node in the cycle has a dependency on some other node in the cycle. So A has a dependency on B, but where is B? B didn't occur here. If B does occur here, then we ask, where's the dependency of B? Where is C? Well, maybe C occurs here. But now we say, where's the dependency of C? Oh, well, darn. A would have had to occur here, but we already said A occurred there. So you can see clearly that there's no way to do this. So if you have a cycle, this is not possible. Okay, so the next question is, what if you don't have a cycle? Is it always the case that a graph that is cycle 3 has this ordering that we're looking for? Now, it's definitely the case that there may be multiple possible answers, right? As just a simpler example to build our intuition. We're going to see right away that, look, there's, if I want want to give an ordering here, right? So obviously I have to do D first, but then I can pick B or C, right? So this is one solution, but this is like another solution. It's easy to see this, that either of these orderings are valid because they don't have any relationship with each other. So it definitely can be the case that the topological ordering is not unique. Okay, but how about, so it's not unique, but does it always exist if the graph is cycle-free? What do you think? Yes, no? Well, you might suspect that the answer is yes, but probably at this point we don't really have like a hard argument for why that is the case. Like maybe you could think maybe sometimes it still doesn't exist even if the graph is cycle-free. But we're going to see that it does. And the way we're going to see it is we're actually going to give an explicit construction for it. First, our construction is going to be inefficient. But then we're going to optimize it, and that's just going to be the standard topological sort algorithm. So, what's a way to do this? Well, okay. So first, I'm going to argue that if the graph doesn't contain a cycle, there's some node in the graph that has no dependencies. Why is that the case? Well, suppose every node in the graph has a dependency, right? Suppose that is true. Then here's what I'm going to do. I'm going to pick an arbitrary starting vertex, let's say A. So, now every vertex has at least one dependency. So I'm going to pick an arbitrary starting vertex, call it A. And then what I'm going to do is I'm just going to go forward, and I'm just going to take the first of my dependencies, which definitely exists because I have at least, we already said that every vertex has at least one dependency. So I'm just going to take the first dependency of A. Okay, let's say it's C. Okay, great. Now I'm going to take the first dependency of C. Let's say it's E. Now I'm going to take the first dependency of that. Let's say it's D. And you see what happens here. If every vertex has a dependency, because the graph only has finitely many nodes, after you continue this chain for long enough, you will definitely arrive at a situation where you have a loop. You have visited for some amount of time, you might keep going and get all unique vertices here, but you can't keep going forever, right? Because the graph is finite. It only has finitely many vertices. So eventually, you will be forced back to some vertex that is the same as you've seen before, and at that point, that's a cycle. So it is very clear that our graph must necessarily have, if it can be solved at all. Like, if we ever find a cycle, we can terminate right away because we can say that there's no way that this can have a topological sort, right? There's no way that this has a topological order. But if we do not find, a cycle, it must be that, this situation would have occurred if not for the fact that we reached something that doesn't have any dependencies. The only way this situation can be prevented is if D, for example, did not have any, if D did not have any dependencies, then okay. Right? Then okay, it stops here. There's nothing to do here, and maybe there's no cycle here. So now we know that if our graph is to have any hope at all of having a topological ordering, we know that there must be some vertex that has no dependencies. So here's the thing. Generally, when vertices a vertex with no dependencies can be safely added to the topological sort, right? Because it has no dependencies. You can't possibly violate the constraint that all of its dependencies need to be satisfied because it's trivially true. It has no dependencies. So any vertex that has zero dependencies, of which there's at least one, can be immediately added to the topological order. And in general, it's better to add things as early as possible because obviously we realize that if we satisfy a dependency, it may unblock other things. Okay, so here's what we're going to do. The first thing we're going to do is we're going to scan this graph and find all the nodes that have zero dependencies, and we'll just go ahead and add them to our list. So in other words, we'll be building our list incrementally. Okay, so what has no dependencies? A has 3, B has 3, C has 1, and E has 1, and D has none. Okay, so D is a vertex here. So we can go ahead and add D. Now here's the kind of interesting insight. Once D is satisfied, it's as if D didn't exist, right? Because once D is satisfied, we can just pretend this is gone. Why? Because any further attempts to do anything here can just treat these edges as if they don't exist because this is satisfied. Like, we don't have to worry about the dependency D. We can have every node forget that it has a dependency on D because that dependency has already been satisfied. So in effect, what this really means is we can just go ahead and delete these edges from the graph. We can go ahead and scan our graph and delete every reference it has to D. Okay, and now we repeat the process. We know that we unblocked at least one word here, and now we just repeat the process. We keep culling the graph. We keep, removing stuff from the graph. And now we're going to make the argument that once again there must be at least one vertex that has no dependencies, because, and we have to revisit this argument because now, like, we deleted some stuff from the graph. Let's make sure it's still correct. Suppose there is no vertex with 0 dependencies. Then once again we can find a cycle, right? By the same method. And if we find a cycle, that cycle exists in the original graph too, because we're never adding any edges to the graph, right? We're only deleting from the graph. So if we find a cycle in this reduced graph, that cycle of necessity definitely existed in the original graph, because we're never adding anything to the graph, right? So if we find something here, then for sure it exists in the original graph too. The original graph is a superset of everything we have left, because we're only ever deleting from it. So if there's a cycle here, like if I were to detect a cycle like ABCA, then it exists in the original too. Okay, so let's keep going. There must, once again, if we have any hope of completing this, there is a vertex with 0 dependencies. Oh look, that vertex is E. Okay, and let's remove all references to E. Okay, is there once again a vertex with no dependencies? Yep. And now, once again, B. And now we're left with only A. And A is dependency free now. And this was actually the unique solution for this graph. We can see that it's clearly unique by the fact that we only had one choice in each stage, right? Sometimes we get multiple vertices that we add during the same stage. Like, for example, let's say this had been the case initially. Then initially you can either add, like, F or D can be the first. Like, initially you would have added both D and F in arbitrary order in this first part. Okay. So that makes sense to people, right? Like, sometimes the ordering may not be unique. There may be many ways to do it. But, we can always find it using just this, like, generative method. Because at every step we're saying that either we're going to make some progress on generating the solution, we're going to find at least one thing that can go here next, or we are hopelessly doomed because there's a cycle. And we already know that there can never be a solution if there's a cycle. And so if we ever reach that situation that there are still vertices left, but there's nothing that has 0 dependencies, then it's a cycle. And we can always even trivially give an example of this cycle, right? Because we just do it by the method I mentioned. Pick an arbitrary vertex and just follow it until you find a cycle. Pick an arbitrary starting vertex and just follow its dependencies until you get into a loop. So topological sort will be easily able, once it reaches that stage, it will easily be able to report what an example of a cycle. So, like, this is obviously very helpful for, like, debugging, right? Like, your libraries have a circular dependency. Here is the dependency, right? Very, very useful. You don't want to just say this graph has a cycle. You want to print out an example of a cycle. The reason I say an example is because a graph may have multiple cycles, right? Of course. I mean, we can easily see that a graph can have multiple cycles, just, like that, right? I mean, clearly there's one cycle here and one cycle here. Okay, so what is the time complexity of this? Like this naive method? It's actually not so bad. I mean, it's bad, but it's not, like, terrible. What do you think it is? Well, so let's consider what we do. We scan, in every step, in every stage, we scan every vertex in the graph. Okay, so that's order D, to just check every vertex and see and check the size of its, remaining adjacency list. Okay, so because we're modifying the graph, we may have to copy the graph before we begin if we don't want to destroy the original input. So we may actually copy the graph before we begin. So that takes order like b plus e to copy the graph. So this is the copy. This is the, and then for every stage, this is like a for each stage. Order B says, we scan all the vertices and we check how many dependencies they have. And okay, so that's order B to find out if any are ready to be added. And if we, if we detect such examples, we have to remove them from everybody else's adjacency list, right? And that actually is going to require order B time because, if for example, we remove B, let's say we have a situation like this, and we're trying to remove B, because this has to be deleted from the front of the array, these would actually all, this would be like a linear time movement, right? Now, we could improve this by storing this in a set, of course, but it wouldn't provide enough of an improvement. But basically what I'm getting at is the total time of removing a vertex can be proportional to can be linear in the size of each of these adjacency lists. And the sum of all such lists over all vertices is just E. So in other words, that's a more complicated way of saying you have to check every edge to see if it should be removed. When you delete a vertex, you have to check every edge to see if it should be removed. So for each stage, you have this order B, find zero dependency vertices. And then you have this order E edge removal step. And so essentially you have order B plus E. So, I'll assume the graph has enough edges that B is small in comparison to E. That's usually a safe assumption. So we'll say that basically for each stage, we do order E work. And so we can see that the time complexity of this algorithm, and this is just order E essentially too, and this is going to be smaller because this is in a for loop and has the same complexity. So essentially this part is also not really relevant. And the real thing is for each stage of the algorithm, we do order E work. And the worst case number of stages is B, because in every stage we add at least one vertex to this. And we're done when we add all of the vertices. So the worst case scenario is, the worst case time complexity is order B, E. And the space required is just like a copy of the graph, so it's basically order E. So this is not too bad. And in fact, this is not really B times E, this is number of stages times E. So if you have a graph that's very large, it can be seen as not having a lot of stages. Like for example, consider a graph like this. Consider, this graph. Something like that. You can have a lot of vertices here, but there's only 3 stages. So, these all have 0 dependencies, and after these are removed, these all have 0 dependencies. So this would actually get processed in 3 stages and wouldn't require VE time, it just requires number of stages times E time. And another interesting thing we can see about this algorithm is it offers us opportunities for parallelizing things. Why is that? Because it's just as easy for us to get this linear order as it is for us to get layers, right? By layers, I mean, I would like to kind of cluster these nodes by which layer they're in. So in other words, I can do these 4 in parallel, right? Like if I have multiple processes, these all have no dependencies, so they can all be done in parallel. And then once these are satisfied, then all of these can be done in parallel. So essentially, this is kind of going a step beyond, and instead of getting the linear sequence, I'm getting a linear sequence where I kind of identify, instead of getting a sequence like this, I basically get the sequence and I say, okay, this is stage 1, this is stage 2, that sort of thing. And what I mean is that these can go into any order, and these can go into any order, and therefore these can be parallelized, and then once these are done, we can do all of these in parallel. So in the case of where I have multiple, threads or whatever available, I might be able to get some parallelization. Of course, some things cannot be parallelized, right? Because I mean, of course, sometimes the number of stages may be equal to the number of vertices. I mean, consider. So here, there's no choice but to sort of like D, C, B, A, and each one is a separate stage, right? Because you definitely have to do D before you can do C, which you have to do before, you know, and so on. Okay. So anybody have questions about this, you know, initial method that I showed? Does it like make sense to people? And do people understand the importance of this dependency sorting problem? So, you know, keep in mind, it applies to other things than just, you know, compilers, right? It applies to other things than just, you know, compiling libraries. You can also, you know, like here's another problem, right? I'm pretty sure I saw this one in college where, you know, you have a bunch of university courses, right? So here's a problem. You have a bunch of university courses. So this is like, you know, CS 101, you know, CS 102 depends on CS 101. Like courses have prerequisites, right? And like maybe you have to take like math 101 here before you take this one. So courses have prerequisites, and a computer science major, or any major, can be seen as some kind of flow of dependencies, right? And you know there's not going to be any circular dependencies. You're not going to say, you need to take this course in order to take, you have to have completed this course before you can take this other course, and you have to have completed that course before you can take the course you need to take in the first place, right? They would never do that. Unless they just didn't want anybody to take the course. I mean, possible. You gotta watch out for that, like, sneak attack by professors, you know. They just want to do their research and they don't want to teach. You have that situation? Yeah, you have to watch out for that. But in any case, like, I guess you could have, what you could legitimately have is like a situation where two classes have to be taken concurrently. But that doesn't really qualify for this kind of situation because two classes that have to be taken concurrently is conceptually the same class worth 2 credits. It's not one, because it's not that one has to be completed before the other. Like these dependencies are like, the class has to be completed before you can begin the other. So, you know, a major can be seen as having like this kind of flow, right? So maybe, you know, maybe you can take first CS 101 and Math 101, then you take like the data structures course, you know, then you take like, you know, operating systems, then you take digital design, and then maybe, you know, after a bunch of courses, you get down to your senior project, and you have to complete all these other ones before you do senior project. So, you know, there's some kind of flow, and this is like an elective, or whatever, CS elective. And so there's some kind of flow like this, right, that tells you like what courses you have to take. And so here's the problem. You should be able to solve it easily at this point, is how can you determine what is the minimum number of semesters in which the major can be completed, assuming every course is offered every semester, which is not usually the case, but okay. You know, you got to simplify a little bit at first. So what is the minimum number of semesters in which this curriculum can be completed? Well, it's equal to the number of layers, right? Because you figure you can only begin like first you consider like what has nothing that depends on it. Well, okay, so senior project. What would it take to basically begin doing the senior project? Well, you have to have all of these, right? I mean, I guess a better way to think about it is think about it in the, well, okay, so this is actually not the best way to think about it because like I drew these arrows like this, but the dependency is actually in the other direction, right? Like, we have been using the convention just to be consistent with what we did before. Like, we've always been using the convention that this means A depends on B. So actually, if somebody gave me a diagram like this, I should be careful to reverse, you know, the arrows in the other direction, because it's actually the senior project that depends on you having completed this course, right? Certainly, CS 101 does not depend on you having completed CS 102. So the direction actually goes like this, and then it makes, you know, kind of more sense to apply it. So, you know, you gotta be careful with these problems that you do it in the right direction. And, you know, you can have any convention you want. You could say A points to B means A has a dependency on B, or you could say that means that, you know, if A points to B, then it is B that has a dependency on A. You can use your choice of convention. Some things may be more convenient than others for various algorithms, as we'll see. But you can choose any convention, but you have to be consistent. So if you've got a diagram of this form and we want to use the convention we were using before, we have to reverse the edges first. And so now we get this, and so what has no dependencies? Well, you take everything you can in the first semester. If you want to get through your major as quickly as possible, right, you take everything you can in the first semester. So this is semester 1, then you take this, semester 2. You can't take any of these yet. Then you take this, semester 3. And now, what once again has no unsatisfied dependencies is this, and so your major can be completed in 4 semesters. Probably not the case for like a real CS major, but yeah. And this assumes that you're gonna like pack yourself with all the courses you can. You know, maybe you have a limit on how many courses you can take each semester, right? And so maybe it's not doable. But this is simplifying it. So classic problem, easily solved, using topological sorting. Okay, now let's think about it. Like, we're not completely satisfied with our algorithm being order b times e. Let's try to improve it. By the way, I do also want to mention that another common application of something like this is basically like data dependencies in like data pipelines. So this is something I see a lot at work, right? Like all the data pipelines I use are like basically described as directed acyclic graphs. So because basically, like let's say you need to do some, before you can do a certain computation, like maybe join 2 tables together, you have to calculate those 2 tables, right? So this comes up a lot in like a data pipeline where like you have some calculation, but before you can do it, you're dependent on other upstream calculations. So maybe like the user logging data has to land, and then I can start the process of joining it with some other data I have over here. So this is one data set 1, this is data set 2, this is data set 3. I have to wait for all of these data sets to arrive, and then I can join them together in this process. And then after I have this join, maybe I can do this additional transform step I have. And then maybe I derive a couple different things off this transform data. And so here I have like a data pipeline, and it's modeled in the same way. It's modeled by directed acyclic graph of dependencies. Like like before I can do this joining step, I need to do these. And before I can do, I need the joining step before I can do this transform step. And then I need this before I get like my result 1, result 2, result 3. So once again, I'm faced with the problem of finding a valid order of execution here. In a lot of like data frameworks, you don't really do this. It figures it out automatically for you, but how does it work? It does this. Under the code, it's basically finding what the sequence needs to be. All right, so how do we improve our algorithm? Well, what was the problem with it, really? So, we had, what was really the problem with our algorithm? It was that we have to do a lot of work to delete a bunch of stuff every time we make progress, right? So, we do have this situation. So let's say this is our graph. But let's say I include this one. So this one has no dependencies. So let's say I include this one. I include F in my list here. Was it really necessary for me to search my entire graph for references to F? No, right? Why not? Because I could have prepared a data structure in advance that would have let me know that the only thing that refers to F is E. So that's the trick here. Like, why are we searching our graph in its entirety every time? You might imagine that that's kind of slow. Let's do this. Let's prepare a data structure that is basically the reverse edges. So this is like a reversed version of the graph. So here we go. We're just going to prepare a reversed version of this graph. Maybe did I do that wrong?
The data C is reversed.
Oh, yeah. Okay. Yeah. Okay. Yeah. So see, so now with this reverse structure. structure, when I try to remove f, so in this first attempt, we'll simplify it later, but in this first attempt, we do also have to keep around the forward graph so that we can, detect, for example, that this has 0 like here we wouldn't know that this has 0 inbound edges, right? Okay, we're also maintaining the forward version of this graph just so that we know that this has 0 dependencies. And, we'll improve on this in a second. Yes, so, well, okay, actually, no, we can drop it right away. So let's say we're just maintaining this version of the graph, right? And, let's say every vertex also just maintains a set of everything that is inbound into that vertex. Okay, so, we have this vertex and we have an f to it. Now using this forward formulation of the graph, we can detect that E is the only thing that could have been affected by this, right? So what we can do is we can just go to E and we can tell, like there's a forward version of this graph that still has this adjacency list, right? So I'll keep this backwards version of the graph here, and I'll also keep like the adjacency list of the forward version of the graph. So the forward version of the graph had an entry, among other entries, has an entry like this, right? And so what I want to do now is when, I want to detect that f has nothing going into it, and then I want to say that, okay, I'll follow f to see where it's referenced from. And now that I know it's referenced from E, I can remove it from here efficiently. And furthermore, I will keep these in a set. You understand why? It's so that I can delete them more efficiently. So now what I do is I find that, I can put f in here. Well, first I have to do like an initial scan. I'm kind of forced to do a scan initially for what doesn't have, first, my very first step is I do have to go ahead and scan the entire graph just to find out what are the things that don't have any, I scan the entire forward graph to find out what has an empty list, right? What has no dependencies. And I note these down. So here I note down that F and D did not have any dependencies. So it'll probably be less confusing if I just put the whole list up here. So E was going to F, A was going to E, and also C in the original formulation, right? A had a pointer here and had a pointer here. Oh, it was also going to B, E, C, and B. And these are all sets so that I can delete from them efficiently. If there were lists, I would have to potentially have elements moving about as I try to remove them. And then, B had D and I guess it just had D going into it, right? And C had, this is why I want to put this up, because otherwise it just, trying to interpret it on the spot gets a little confusing. Yeah, so E was going to F, A was going to E, B, and C. B was going just to D. C was going to D and E. In the forward formulation, C was going this way and this way. And what am I missing? F. Yeah, F was an FT in the forward formulation.
So D is on.
Huh?
D is on.
Yeah, I don't have D yet. And then D was also FT. That was the initial forward formulation. Now, here's the thing. So initially, I do have to do a scan to check what's empty. So I get F and D. Okay, I'm going to store that in a list. This is like a queue kind of thing. So this is actually going to resemble BFS, and you'll see why in a second. So this is just like some queue. Okay, so I know I have to process F and D and add them to the topological sort. And so here goes my sort. First, I take F out, and I add it over here. And now I can follow this reverse graph to figure out where to delete F from. So F goes to E, so I go in here and I delete it. And I can do so quickly because I know which set to delete it from, and it's a set, so I can delete from it quickly. And then, only when I actually edit this set, I check, is this set now empty? And because it is, because E has now become empty, I mark it as another node that I know to be empty. And at any given time, the nodes that are in this queue and in this topological order are the only ones that are known to not have dependencies, right? Because initially we did a scan and we found out everything that doesn't have a dependency. And the only way that other lists can come to have no dependencies is if we actually delete something from them. And every time we delete, we check if it's become empty, and if so, we add it to the queue. So this has all of the things that have no dependencies left. Between the queue and what's already in the sort, these are all the things that have no dependencies. And now we just process the next thing from the queue. Like we take D and we transfer it over here. And we follow this reverse graph to find out what referenced D. C and B were referencing D, so we go here and we delete. B and C were referencing D, so we go and delete. And as we deleted this one, we noticed that B has gone empty, and so B was added to the queue. However, C was not added to the queue because C still has more dependencies. We only add to the queue things that are ready to process. Now we're going to proceed with E. We're going to transfer E over here. And we're going to search E's backwards dependencies. So we see that we can delete that. Okay, so this doesn't get added because it still has dependencies. Now we process B. So we follow these two pointers to C and A. So this is gone. A still has dependencies, so it's not added. And this is gone. And now this is added because it has no dependencies. E got placed over here. And now we process C. C goes to A, and so we remove it from here. Now A has no dependencies and gets added here. And finally we process A, and A has nothing else to visit, so it's does nothing, and it gets added here and it's done. And that's our solution. It was not the only solution, right? Because we could have processed these two in any order. So this is how this algorithm works. Now, what is the time complexity here? It's actually quite good, right? Because now we're removing stuff from the graph very efficiently. That's the key part. How efficiently? Well, we have to build this reverse copy of the graph. Okay, so that's just a linear time though. We copy the graph in order E. What else did we do? We might have to restructure these lists as sets. That's another copy-like operation. We'll include it in here. It's still order E. And then we have to do one scan through the graph to find everything that's empty. That's order V. In the initial, basically build the initial queue, the initial empty list. That's order V. Just scan and find everything that's empty here. And then finally we may have the actual processing, right? And what gets done in the actual processing? Well, every time we take a value from the queue, and we're going to assume the queue has efficient dequeue from the beginning of the data structure. That's what it means to be a queue. We have to make sure we don't use a list for the queue, right? Because lists don't have efficient removal from the beginning. We have to make sure we use a true queue that can support efficient dequeue and efficient dequeue from the beginning of the queue and efficient enqueue to the end of the queue. We have to make sure, that's the case. And if we're using that, then how long does it take to process every element? Well, we remove an element from the queue, and we append it to this other list. That's our solution, right? We append it somewhere in our solution. We append it to the end of this list, so that's an efficient order 1. So all of this, taking an element off here and putting it in here, is order 1. And then for every edge in this reverse graph, you have to do a step, right? For every edge in this reverse graph, you have to do a lookup in here and a set removal. And that's like an order 1 operation, right? Order 1 to look up the set, and order 1 to remove the entry. So it's order 1 completely to do this whole operation. And so essentially, we are doing an order 1 operation for every edge that is in this reverse graph, right? Because for every edge that's in this reverse graph, we'll do this operation once. If I have an edge from E to A, then that means at some point I will go and I will say E, A, I will go to A, and I will remove E from here. And that means that I'm doing an order 1 operation once for every edge in the graph. So this step is order E. So the main algorithm is order E. And the time it takes to NQ stuff, again, like every vertex can only be NQ'd once, and there's only V vertices, so again, this is like only order V. And so all the other terms are lower, and basically the total time will be order E. Order E is the highest factor you have anywhere. There's nothing that's not linear. So why do I say this algorithm is kind of like a BFS? Well, maybe it's clear, because essentially we have, we have a queue. We're processing things in the order that they get added to the queue. And in this case, we happen to be building a solution as we're processing things. So the real difference between this algorithm and BFS is like, remember in BFS, we basically add something to the queue the first time it is visited. This one is kind of different, right? We add something to the queue when it's been visited the maximum number of times. When it's been visited from every possible spot. Like if A, if A had dependencies on E, F, and G, A will have to be visited from E, F, and G before it can be added to the queue, before it has 0 dependencies, and it can get added to the queue. So that's one way to think about it. It's kind of like BFS, but except adding something to the queue when the first time you see it, you add it to the queue the last time that you're going to see it. You add it to the queue when it has nothing else that's going to point to it. Now, before we try to see any pseudocode for this or anything else, I'm going to show you a simplification to this. So I wanted to show it like this so you could understand it conceptually. Now that we understand it conceptually, we can simplify this more and make this really easy. So I'm going to observe that these sets are not actually necessary. Why not? Because, well, in these sets, we are never actually using the set membership operation, right? We are never actually asking a question like, is this vertex really in the set? We're never asking that. Every time we go to remove a vertex from one of these sets, we know that the vertex for sure is going to be in that set, just by virtue of how these sets were generated. So it's never a conditional operation. It's always like, when I go to remove something from one of these lists, I know for a fact that it's going to be there. So that actually means that there's no reason for me to even store these values in the sets. I can just store a count. This is called reference counting. So what I can do is when I initially, see this, if A, I'm not going to use the right numbers here, forget about this graph, but when I initially see this, I can just go ahead and associate this, each node with a count. How many dependencies does it have? So E has 3 dependencies, and A has 2, and B has none, and C has 1, F has 1, and D has 0. Then I'll just initialize the map like that. I will still need the reverse graph. That part is important, because you still need to know which of these counts to decrement, right? And then that will mean that, okay, first I will take this B and D, and I will put them in my queue, right? So I will take B and D, and I'll put them in my queue. And I'll have a set. Not set. This is the sequence. And this is initially empty. So I'll initialize it in the same way. And then what I'll do is, when I process this B, let's say my reverse graph, among other things, this is just a section of it, says that B is referenced to by A and by E. Right? And then what I'm going to do is I'm just going to go here and I'm just going to decrement these counts. Just saying that, okay, each of these now have 1 dependency less because B has been satisfied. And then as I decrement the counts, I check has anything reached count 0. And if it has reached count 0, I add it to the queue. In this case, nothing reached count 0, so I wouldn't add this to the queue. I would just transfer this over here. And now I proceed with D. And maybe in the case of D, I find that D also was referenced to by A. And then when I process D, I decrement this count. And that would lead me to add A here, and then transfer this over here. And this keeps going. What happens if your queue runs out of elements? What do you think? If your queue ran out of elements, what does it mean? So, if your queue is out of elements, between the queue and the ones you already have, that's everything that has 0 dependencies, right? So if your queue has no elements, it means that there are no 0 nodes. Now that can be one of two cases, and that means that at the end of this algorithm, you're going to have to check which of these two cases you're in. Either everything has now dependencies, everything now has 0 dependencies. That just means you're done. Everything has been given, like basically if S now contains every node, if the reason your queue is empty is because S is full, S has one of every node, then your algorithm's finished. If the queue is empty and S does not contain every node, that means there's a cycle, right? That means that you still have things that have non-zero dependencies, dependency count, but there's nothing you haven't processed yet that has a 0 dependency count, which means there's nothing you can process next because everything else is stuck in a cycle. Yeah, and then how would you print out that cycle? Well, of course, you could just filter out all the ones that have at least one dependency and use that method I discussed earlier. Pick an arbitrary vertex, go to some of its dependencies, and so on, right? And then you would find the cycle. The same argument we use to justify the very fact that this method works, or that this method cannot, you cannot find a solution if there is a cycle. And or the same thing we use to justify that if nothing has 0 dependencies, then there definitely is a cycle. So you can apply that same argument to find the cycle. Okay, so here's a quick problem. This is a very classic problem. Interviewers are not so much asking this problem because it's very well known. And this problem is straight out of cracking the coding interview. I believe this problem appeared there. And this is like the classic alien languages problem, if you remember that. So what's this problem all about? You have a text you have a dictionary in an alien language, like a dictionary as a like word dictionary, not like hash map, right? So you have access to the dictionary of some language that you don't know. It's like some alien language or whatever. And let's say you've been able to identify, that their language has some number of symbols. I mean, it doesn't really affect the problem, so let's just for ease of writing it, let's say their symbols are, they have 26 different symbols, and we kind of translated them from A to Z. Like we just kind of arbitrarily substituted in A to Z. So let's just arbitrarily say the alien language can be written as, a sequence of letters A through Z. And you'll see that it doesn't really affect the problem. If you have 40 characters instead of 26, it doesn't really matter. So let's say, we have their dictionary, and it looks like this. And the words, we know that the words are sorted lexicographically. So let's say we have, first we have a word like this. These are just symbols, so, we don't know, if they have any vowels or, how it works. But so let's say you have a dictionary that looks like this. And then you have, let's say you have some sequence like this. So let's say this is your dictionary, and now you want to basically find out what is the. So there's not going to be enough information to solve it here, but what is the ordering of letters in their alphabet, right? So here you can see that if this is sorted lexicographically, in increasing lexicographical order, it has to be that B comes after C in their language. So unlike English, where B comes before C, here B would be coming after C. So so you have this text and you want to figure out what is the ordering of letters in their language, and you also want to figure out if that's if there's no unique solution, you want to figure out what is one possible solution. What is one possible ordering of letters that is consistent with this example, right? Okay, so this is actually a topological sorting problem because we can think of it this way. We can think that, the dependency here is basically which letter must come before every other letter. We're basically looking for a topological ordering of letters. And what we have here is that we have a little bit of information about what that ordering should look like. So actually, this first string gives us no information. Because this first string, like this would be true regardless of the sequence of letters, right? So this, looking at these two words, it actually gives us no information. Because, assuming you always have the rule that space comes after, any letter comes after space, then this gives us no information. So, okay, forget about this one. Now, what information does this give us? Well, this teaches us that B comes before C. So C is basically dependent on B, in the sense that B should appear in the topological sort before C does. And we have no other information from here. We can't tell whether D is first or A is first, right? Because this would be true, the first letter is compared first. So as long as we know that that's the rule in the alien language, we know that, this only tells us that B comes before C. D may or may not come before A, we don't know because this dominates. Okay, now let's check out the next one. This one tells us that B comes before A. And then maybe we have another example that says A, D, X, R, for example. And this one here, what we would have to do is we'd have to, compare the letters between these examples until we find one that differs, right? Because that's where the information is. It doesn't tell us anything that these A's are the same. Of course they are. Of course all the A's are going to be put together. But we know that these are different. And from this is the first difference, and here we see that it must be that D comes after B. So in other words, we now know this about our language. This represents the state of our knowledge about the language. Now you might wonder, why are we only comparing these ones? Right? Why are we only comparing adjacent words?
Sure, this is the right direction.
Yeah,
Medium axis.
Hold on. Sorry, yeah. Yeah, that's right. I drew the arrow in the wrong direction. What I meant is, okay, so my convention is I'm going to draw an arrow towards the thing that's less. So, here we had the conclusion that C is less, so we should have drawn this arrow. Here we had the conclusion that A is less, so we should have drawn this arrow. And here we have the conclusion that B is less, so we draw this arrow. Okay. What? Did I mess it up again?
You get CBA.
Okay, hold on.
CBA is the equivalent.
Oh, I forgot to update this arrow, yes.
Yeah.
Okay, let's do it over one more time, I keep messing up. So here we get the conclusion that C is less, so we point an arrow towards it. Here we get the conclusion that A is less.
B.
Oh, sorry, yeah, that's what I did wrong. I looked at the wrong one, yeah. Okay, here we got the conclusion that B is less, so we point an arrow towards it. And here we get the conclusion that, this one's equal, so we don't get a conclusion here, and here we conclude that D is less. D is less. Yeah, I drew the arrow in the right direction. Yeah, so, exactly. Yeah. B is less, and therefore we draw the arrow this way. Okay, yeah, so we have A, B, C in this order, and then we don't know the relationship between C and D. And let's say the next string is A, D, R, D, or something. And so now here we don't get any information, and now we've concluded that the relationship between R and X is such that R is greater, X is less. So now here we have 2D letters, and we have something like that. X is less. And then maybe in the next one we have something like this, which allows us to conclude that, A is still greater, so R is less, and now we have something like that. And then eventually, as we process more and more of these words, we build this into a knowledge graph. And you might wonder, why do we only compare adjacent pairs? Why don't we compare all pairs, right? Why are we comparing, only this and this and this and this? Why shouldn't we compare every pair? Well, part of it is that if you compare every pair, this algorithm is at least n squared, right? And you can show that there's actually no additional information. information that would be derived from doing that. Like you can show that, you can basically show a result where you say that, like, pick 3 results, and let's say I've already, like, picked any 3 results in order, and I'll argue that if I have this information comparing these 2, and I have this information comparing these 2, then this information comparing these 2 is redundant. You have to kind of show that, but intuitively it makes sense, but you actually have to like show that. And then based on that argument, you can argue that all you need is like comparisons between adjacent words. So yeah, based on that argument, you can eventually conclude that all you need is to do is compare adjacent words, and that will give you all the information that comparing all the pairs of words would have given you. But that's a separate thing we have to argue, but just to speed us up, I'm going to tell you that it's true. It's not hard to show this. Basically, you just make that kind of argument that I just made, that, consider 3 results, and you can see, and you will see that the information for this is redundant, and so we only need to hold on to this pair and this pair, but then we can kind of shrink it further down to just comparisons between pairs. And then we draw this graph. I think kind of like the career cup solution, if I remember correctly, not career cup, but cracking the coding interview, I think they completely gloss over this point, if I remember correctly. They're just like, oh yeah, of course we're going to compare every 2 adjacent entries. And they kind of completely gloss over this point of like, yeah, why is that safe? Why does that reveal the maximum amount? But anyway, so, you got this, and you get some graph, right? And then, we're going to apply topological sort to this graph. And, that will give us, like, assuming the dictionary is consistent, right? Assuming there's no circularity that's implied by the dictionary that then has gotten translated over into this graph. Assuming that's consistent, it'll give us one possible ordering of the words in the language. How do we know if it is the unique ordering? Like, so here the ordering is not unique, right? Because we don't know any relationships between these variables. Like, we don't know if, like, R comes before or after C and D and whatever. So here it's not going to be a unique solution. We can just get one possible solution. But how would we know if the solution is going to be unique? Yeah, exactly. There would be only one choice at every point, right? There would only be one thing. Well, remember, the arrows are heading towards the thing that's least. So the first thing is going to be like something that doesn't have anything, that is known to be less than it, right? So the first one here could be any of these. Like it could be any of these for all we know. But if there's only one choice, then you put that one down and then you keep going with the topological sort. And if there's only one choice in each layer, then you know for a fact, like if after you take this one, there's only one other thing that can be next. Then you know for a fact that you must have constructed the unique sequence. If ever you come to a point where there were 2 choices, then clearly which one you decided to put first was arbitrary. So in that case, in that case, your solution is not unique, and you need more words in the dictionary to find out the true order of those letters in your language. And if you can try this, you can download like an English dictionary and you can try this algorithm, right? And I'm pretty sure that there's enough information in the dictionary that you will be able to unambiguously conclude that, this ordering of English letters is A through Z. Unless of course the dictionary made a mistake, then you might get a circular dependency. I wonder if they like run their dictionaries against this to like validate the dictionary. Probably not. Probably not. I mean, it's not the best algorithm for checking that anyway. Like, you could just compare the letters one by one, of course. This is more for like reconstructing an unknown order of letters. So yeah, so you can see how you can use topological sort to do something like this, where you have ordered, you make the relationship that you're, that you're modeling. The dependency relationship is basically, which letter comes after which other letter. And then you basically say, I want to require that this letter come first before this other letter. And then in the end, you'll get a graph, and you'll seek a solution to that graph.